Assalamualaikum warahmatullahi wabarakatuh. Today I'm Prof. Hada. And today I'm going to talk to you about the uses of organometallic compounds. One of the most important properties of organometallic compounds are it's able to catalyze a lot of reactions. Now, the ability of organometallic compounds to undergo the combination of oxidative addition and reductive elimination enables them to act as catalysts. In oxidative addition, the newly added ligands are brought closer to the original ligand, allowing chemical reactions to occur between them. I hope you remember what is oxidative addition. It is one of the reactions that can be undergone by organometallic compounds where small molecules are added into the compound. And reductive elimination is the reverse of oxidative addition, where by eliminating small molecules from the organometallic compound, the metal center undergoes reduction. The oxidative addition just now, by adding a small molecule into the compound, oxidation will occur to the metal center. Now, if you can imagine that the compounds are buses, yeah, you get one reactant going up. So recall what Dr. Nizam explained to you last time on the deuteration of benzene. Benzene goes up onto the tantalum reaction. Here it is. Let me scroll down. There you go. You have, first of all, this is the deuteration reaction of benzene using this compound where it has 1 tantalum, 3 hydride, and 2 cyclopentadienyl. Now, the reaction that is originally 18 electron will first undergo reductive elimination. Now, this is a reductive elimination where 2 of these protons or 2 of these hydrogens are eliminated as a hydrogen molecule, producing a species of 16 electrons. So you have tantalum here, and 2 electrons from there, 6 electrons from there, 6 electrons from there. So you have 16 electrons. How do you count the electrons there? You understand, yeah? So once this species is produced through the reductive elimination, it is ready to go through the cycle of oxidative addition, where now benzene goes into that compound. When benzene goes in, it will make a phenyl olefin ligand here, and the hydrogen that originally sat here, sitting here on this carbon, now goes onto the tantalum. So you have an 18 electron species here where a benzene has attached itself into. Remember the analogy of the bus. Now the bus is now having 1 passenger. Now the hydrogen is not required in this reaction. Hydrogen is not required. It is, we want to replace all the hydrogens in benzene with deuterium. So when the 2 hydrogens are not required, they will be eliminated. In the elimination process, you lose 2 of these protons, and you get a hydrogen molecule being kicked out, and you again left with a 16 electron species through this reductive elimination, RE. With this insufficient electron in here, deuterium can go in. Now, deuterium is the desired thing in the compound that you want to in the reaction that you want to carry out. So the deuterium goes in. So you have this 18 electron species. If you still recall, how do you count 18 electrons? How do you recall 18 electrons? Where is tantalum? What is the oxidation state of tantalum here? Yeah, so I would like you to try and count the electrons in here. If you have any problem, please go through your notes again and see how you count the tantalum. This is the fifth process. When you have 18 electron, it is again ready for a reductive elimination. Now, can you see this is Re, reductive elimination. This is OA. This is another Re. This is another OA. And this is Re again. In the fifth step, in the reductive elimination, what is being eliminated is a benzene with one deuterium attached. It was originally, if you can recall here, it was originally benzene with 6 hydrogen. Now you have a benzene with 1 deuterium and 5 hydrogens left. Now what you have here now, this monodeuteurated benzene will go straight onto step number 2, attach itself onto this particular species, and then the proton is eliminated, and then deuterium goes up. The deuterium will react to go up to this second step. Second deuterium, the reaction will happen 5 times. So until all of these hydrogens are being replaced with deuterium. So that is what Dr. Nizam had gone through with you. Okay, I'm going to show you some calculations of electrons for this species and that species. So it becomes such sort of a revision for you. So here I have made some calculation. It is not in your notes, so please add this into your notes. So in here on this box, I have shown you the calculation how the 16 electrons. I'm sure this is very easy for you to do, but I just would like to do a quick recap. So this is the species that had undergone reductive elimination to eliminate 2 protons, produce this 16 electron species. So how do I get 16? So if we do the usual way of calculation for the electron count, you have 2 cyclopentadienyls here. There you go, 2 Cp, which carry a charge of 2 times -1, which is a -2 charge. And each one of the cyclopentadienyl carries with it 6 electrons. So 2 of them will carry 12 electrons. And then you have one hydride here. Here's your hydride with a charge of -1 and 2 electrons. And what about the tantalum? What is the oxidation state of your tantalum? Well, I put it here as 3, but how do I get 3? You just have to, this is, I'm sure Dr. Nizam has gone through with you, -2 -1 plus x is equal to 0. Why 0? Because this whole species doesn't carry with it any charge. So x -2 minus 1 equals 0. This is Form 1 mathematics. So you get x equals to +3. So the oxidation state of tantalum is +3. So how many electrons does that carry? How do we know how many electrons would tantalum 3 carry? You just go back to your periodic table. So this is a snapshot of the column number 5 in the D block of the periodic table where you find tantalum. Tantalum is just underneath vanadium and niobium on the 5th column. So tantalum with no oxidation state, or tantalum 0, has 5 electrons. With tantalum 3, it loses 3 electrons, leaving you with only 2 electrons. So if you count the electrons, you have 12 plus 2 plus 2, that is the 16. So it is very clear how this species is a 16 electron species. And go to the next species where you have a benzene ring added onto the tantalum species. In the oxidative addition, you get this 18 electron species. Again, go through the same calculation. 2 cyclopentadienyls, 2 hydride, 1 and 2, 1 phenyl. Each one of the phenyl carries with it -1 charge and carry 2 electrons. The tantalum, you go through the same exact calculation as the one in here. So you get X, which is the oxidation number of tantalum in this case, is +5. With all the 5d electrons lost in the tantalum, you get 0d electrons. So you count those electrons, you get 18. So that is how we get the 16 electrons in here and the 18 electrons in there. So I hope it is very clear for you how deuteration of benzene occurs. It is through a cyclic reaction or cyclic process where reductive elimination happens, followed by oxidative addition, followed by another Re, another OA, another Re, and do that 5 times more. So you get all your protons in your benzene being replaced with all deuterium. So that's clear. Yeah. So that is the easiest example for catalysis. Next, I want to go through the second example with you. I'm sure Dr. Nizam also has gone through it with you, which is the Monsanto acetic acid process, where you have, it's really very easy. The Monsanto process is the process to produce acetic acid, where carbon monoxide is reacted with hydrogen. The mixture of these two gases is called the syngas, not SIN, but SYN, syngas for synthesis gas. In the presence of copper and zinc amalgam, you get methanol. It's really very easy reaction. You get methanol done. And from methanol, this is where the Monsanto process is showing its beautiful, elegant cycle. When you add into this methanol some carbon monoxide in the presence of rhodium and iodide, so this is your catalyst, 180 degrees C, 30 to 40 atmospheric pressure, lo and behold, you get your acetic acid. So here are the steps. I'm sure Dr. Nizam has gone through with you also. So step 1 is when your methanol reacts with HI. Where do I get HI? It's here. Yeah, you get HI. So it undergoes a substitution reaction where the OH is being replaced by the iodide in your methanol. So you have iodomethane here with water. And then what happens here? There you are. That is your methanol added with your hydrogen iodide or hydriodic acid just now. It's really very easy to read this. This is just an arrow where you don't see the head of the arrow, it is the reactant. Where you see the head of the arrow, it is the product. So methanol plus HI, you get water with iodomethane. It's just simply that reaction, this reaction here, written in this way. Now, when you get your iodomethane, the iodomethane will add itself onto your rhodium catalyst. This is your catalyst where you have a rhodium in the middle, 2 carbonyls and 2 iodides with a minus charge. If you count the electrons like we did up in this example here, oops, too far ahead. Yeah, if you do the same calculation, you're going to really prove that there are 16 electrons in this species. So your iodomethane will add itself onto this rhodium species, the catalyst. That is your methyl, that is your iodide. It's adding itself in oxidative addition. So you get a 6 coordination number with 18 electrons. So what happens next is a little bit more complicated than your deuteration of benzene just now. You get addition of carbon monoxide. This is carbonyl insertion. I'm sure Dr. Nizam also has gone through carbonyl insertion with you. The carbon monoxide inserts itself between the rhodium and the methyl group to make this. This is an aryl, becoming an aryl. So by adding this or inserting this carbonyl, there is no change in the oxidation state of the rhodium. It still remains the same as it was here, which is +3. Still an 18 electron species because this is still a 2 electron species, just like that one. So what happens here is the elegance of this Monsanto process is it is bringing, because what do you want to get at the end of it? You want to get ethanoic acid or acetic acid. You need a methyl, you need CO next to the methyl, and you need OH. So by putting in first the methyl, yeah, the methyl first come into here, and then the carbonyl, what you get now is the methyl is seated next to the carbonyl. So being in close proximity allow the methyl and the carbonyl to react. So what happens next? What happens next is another elegant move in the catalysis where you have reductive elimination of the CH3, the CO, and the I. Where does the I come from? It comes from here. So these three are getting eliminated from this catalytic species or from this bus. As I was telling you, it's like a bus. You have one passenger coming up, the next passenger goes up and seated next to your methyl. And then when they want to alight the bus or when they want to go out of the bus, they go out with one iodine. So what happens to that iodine? Here, beautiful. This is the species that got eliminated from the catalytic species, making the catalytic species return to what it was, ready for the next HI. What happens is, if you can recall, water that was produced is being reacted with this eliminated product to reproduce your HI and what you really want, which is the acetic acid. So here, as a Monsanto process, this is a very, very beautiful illustration of how a few reactions get together and produce acetic acid very, very easily in the in an industrial scale. So that's the Monsanto. So two reactions I have um, uh, I've done a revision with you. I hope you understand the two very well now. So next, what I want to go through with you is the next example, which is Wilkinsons catalysis for hydrogenation of alkene. Now, usually in the industry, when you want to hydrogenate an alkene, really it's like a process of, if you know, the production of margarine, for example. Yeah. Alkanes have very low melting point compared to alkene. Alkene is more fluid, more liquid. So hydrogenation of alkene can also be carried out using coordination compounds. One of the examples is using the Wilkinsons catalyst. Now, what is a Wilkinsons catalyst? This is your example 3, just to recap. Yeah? The example 3 for the use of organometallic compound as a catalyst. Now, what is a Wilkinson catalyst? Wilkinson catalyst has this formula. It's a rhodium with 1 chlorine and 3 triphenyl phosphine. It is produced by a Nobel laureate called Sir Geoffrey Wilkinson. Sir Geoffrey Wilkinson won a Nobel Prize, if you can still recall, together with Fisher for his work in ferrocene, yeah, in kerosene. So Sir Jeffrey Wilkinson also has come up with a compound RHClPPH33. It is called the Wilkinsons Catalyst. Now, what is the use of this Wilkinson catalyst and how is it produced? It is produced through the reaction of uh, trichloro, triaquarodium in the presence of ethanol with triphenylphosphine, and this is how you get your catalyst. And how does it, what is the action? What is the action of this Wilkinson's catalyst as as um, as something that could speed up a hydrogenation process? So have a look here. Now that is your Wilkinson's catalyst. It is a 16 electron. Now please go back and count the electrons. It's really very easy how to count the electrons. If you have a problem, please let us know. Either the museum and I or some of your friends may be able to help you. Now, the first thing that will happen to this Wilkinson's catalyst is it's going to undergo step 1, which is a simple elimination of a triphenylphosphine. So what is step 1? Undergoes dissociation of one triphenylphosphine to give a 14 electron complex Q. So it eliminates triphenylphosphine to become this complex Q, from complex P to become complex Q. So this is the 14 electron, count the electrons, no problem. So it is now ready to receive hydrogen, because the reaction that you want to do is the hydrogenation of alkene. So what do you need? You need hydrogen, obviously, and you need alkene, because you want to hydrogenate the alkene. So hydrogen goes in first. What is this reaction? Step 2. Can anybody guess? It is an oxidative addition reaction. Why do I know it is an oxidative addition? Because from 3 coordination number of rhodium, it becomes 5 coordination number. So 5 coordination number means they are added. There are 2 ligands added. And from rhodium oxidation 1, it becomes rhodium oxidation 3. If you don't know how it becomes that, count the oxidation number, just like the way I did it up here. Where is it? Sorry, on page 36. This is how you do the count. Now, once step 2 is completed, you get complex R, where complex R is a 16 electron species, and it is ready for addition of the next reactant, which is an olefin or an alkene. So this is the alkene, in this case, it is a propene. The propene adds itself onto this rhodium bus or rhodium catalyst. That is your alkene. And that is the hydrogen that sits here. Oh, no, there's no hydrogen, because the alkene added onto this compound through the double bond. So you have an 18 electron species, complex S. So what is the beauty of this? You have your alkene and your hydrogen sitting next to each other in the same molecule. They are seated next to each other in the bus. So this hydrogen is going to hop onto the olefin. This is what it will do. So this double bond is destroyed. Step 4 is called intramolecular transfer of hydride from the metal to the olefin in the complex S. So the hydride or hydrogen is transferred from the metal to the olefin to produce complex S. So you have your complex S here, from complex S to produce complex T. So from olefin, it becomes an alkyl now. It becomes propyl. It's no longer propene. So once it becomes a propyl, You have CH2, CH2, CH3 here. Next, it will get eliminated. Reductive elimination, it runs away with this proton, this carbon, 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 and the hydrogens, all this propyl is eliminated along with a propene to produce a propane. There you go. From a propene here, undergoing this process, it becomes a propane. So it's really very, very beautiful. The process is beautiful. So in eliminating the propane, your complex Q is regenerated. So complex Q can then go on and take one more hydrogen, take one more propene, the intramolecular hydride transfer will occur and reductive elimination. So all your propene will become propane. So that is the beauty of the Wilkinsons catalyst, where hydrogenation can occur in a very, very easy way. So you have catalysis happening in that way. So that is example 3, which is Wilkinson's catalyst for hydrogenation of alkene. So if you put an alkene with Wilkinson's catalyst, what you are going to get is hydrogenation. So let's have a look at the 4th example. The 4th example is also an alkene, but this is Wacker oxidation. This is oxidation, not hydrogenation. So you have the alkene is being oxidized in the Wacker process to become aldehyde. If previously Wilkinson catalyst will change your alkene into alkane, now Wacker catalyst change your alkene into aldehyde. So this is the process. This is the overall Wacker process, where you have here is not a propene. This is an ethene in the presence of a palladium catalyst, palladium Cl2, and a co-catalyst. This is your co-catalyst. Your copper chloride is a co-catalyst, and water and oxygen. You're going to get an aldehyde. So how does that happen? Have a look at this. So that is your palladium chloride. And this L is any ligand. It can be any ligand. It can be also hydrogen or hydride, it doesn't matter. So you have palladium 2 chloride. You are going to have your alkene being added on into your palladium. So that is a simple addition. That just like here, if you can recall, this is a simple addition there. And once that is added, there is a chain reaction where water, the electrons from water will do a nucleophilic attack onto this carbon here, because it is already a partially positive charge. And then you have the electrons hopping onto the palladium. What do you get here is the palladium will be then added on with your alkene that has water added to it. And again, the second lone pair of electrons will collapse onto that bond, and then this hydride is going to attach itself there. So what do you get in the end is a hydride shift. This is called a hydride shift, where L, again, as I was telling you, it can be another ligand, it can be a solvent. Yeah. So you have a beautiful array of movement of electrons in here, hydride shift, and in the end, this alkene is oxidized to become an aldehyde. Now, this is eliminated, the aldehyde is eliminated, leaving you with your catalyst species not quite ready for the next cycle. It is not in this form. So to change this catalytic species into there, you need your co-catalyst. Yeah, your co-catalyst. It is going to reduce reductive elimination of a HCl, hydrochloric acid, to produce that. And then the co-catalyst, which is your copper chloride. Remember, I told you that there's a co-catalyst in here. The co-catalyst will react. This is copper 2 to become copper 1, and the copper 1 is going to just the copper 2 is going to react with your palladium just now to produce your catalytic species, and then the copper will become copper 1. Yeah, this is the co-catalyst reacting with your palladium to produce your species that is ready for the next cycle. But copper 2 become copper 1, and in there will react with this HCl. Remember, there is an HCl in here. It will react with this copper 1 to reproduce your copper 2. So you effectively have two cycles. Two cycles happening. This is the main catalytic cycle, and this is the side cycle where the copper is treating your palladium after the end of this big cycle for the next cycle. Yeah. So first you have a complexation, and you have a nucleophilic attack through water where HCl is removed, and this is going to create a complex that allows for hydride shift. And after hydride shift occurs, you get elimination of the product that you desire, along with the catalyst species that needs to be regenerated, ready for the next cycle. And that regeneration is happening on the side here using your copper co-catalyst. So that is again another elegant reaction where you get organometallic compounds catalyzing the conversion of alkene into aldehyde in a Wacker process. So that's it. With these four examples, your CHM676 is done. And I'm glad that I have the opportunity to contribute a little bit in the last lecture. So you can go through some of these exercises just to do some revision, go through the various past year's papers. That's going to help you a lot in going through the final exam later. And that's it. I'm done. Thank you very much. And I wish you all the very best. And I hope every one of you will graduate successfully this semester. Bye. Assalamualaikum warahmatullahi wabarakatuh.